In this video, we are going to prove one of the most important concepts of the Laplace transform, which states that the Laplace transform of this function, this is quite strange to what we have been doing. This is the Laplace transform of the function f of t divided by t, which is quite strange. We are supposed to prove that the Laplace transform of this function is equal to the integral from s to infinity. This s here is our Laplace variable, s to infinity of f of u du. So if you want to know why the famous Dirichlet integral, which is the integral from 0 to infinity of sine of, let me use x over x dx, this one evaluates to pi over 2. So we can use this concept here to prove the result of the Dirichlet integral. So what I'm going to do, I'm going to go ahead and then prove this, and then we will use that to solve some complicated integrals, and then also find the Laplace transform of some strange functions, that is a particular function f of t divided by t. So we are going to prove this from the right to the left. So that is, I'm going to start from the right here and then show that this result is equal to the result on the left. Cool stuff. So let's start with the definition of the Laplace transform. Let me switch colors. So the Laplace transform of a function f of t, this is now familiar. So this is the integral from 0 to infinity of e to the negative st. This is multiplied by the function f of t and then dt. This one is the same as capital F of s, right? We know this. Now this is capital F of s, but in our proof we are asked to show that this one is equals to the integral from s to infinity of f of u, right, du. So permit me to write f of u here. So f of u, if f of s is equals to this, the difference is the s here, right? So I can write f of u like this. So f of u is going to be the integral from 0 to infinity. Everything stays the same, so we have e to the negative. So instead of s, I'm going to write ut, and then I'm going to have f of t and then dt. The only difference here is the s and the u. That is the difference between f of u and f of s. Cool. So now what do we have to do? We have to integrate this function f of u from s, the Laplace variable, to infinity with respect to u. So now let's do that. So we are going to integrate. So we are going to integrate from from s to infinity of f of u with respect to the variable u, right? And this is equal to, so we are going to integrate the right hand side as well. The integral from s to infinity, then the integral from 0 to infinity of e to the negative ut multiplied by f of t and then dt, but don't forget the du, right? So then you put du here. So this is like a double integral. So it's a double integral, so do we have to worry? So that means that this right hand side, the integral from s to infinity of f of u du, this is equal to what exactly? So the first integral is with respect to t, right? That is dt before du. But we don't know the functional form of what this function. We don't know what that function is, so we can't integrate because this function is unknown. We can only integrate first with respect to u, because this one we can easily integrate this, right? So I'm going to switch the limits of integration. And fortunate enough, the region upon which we are integrating is rectangular, so we are integrating over a rectangular region, so we can easily integrate switch the limits of integration using the Fubini's theorem. So the Fubini's theorem, theorem. So you can easily switch the limits of integration because we are integrating over a rectangular region. So I'm going to integrate from 0 to infinity, and then the first one is going to be from s to infinity. Then I'm going to have e to the negative ut, then f of t. So what I'm integrating first is u, and then later on with respect to t. Right, so I'm just switching the limits of integration. Nothing strange, using what we call the Fubini's theorem. Right, so the integral from s to infinity of f of u then du. This is equal to, so the integral from 0 to infinity, this one is with respect to u, so this function has nothing to do with u. I'm going to bring it here, and as f of u, then I am going to integrate from s to infinity of e to the negative ut, then du, and then dt, like this. Okay, cool. So now let's integrate. So from s to infinity, then f of u du. This is equal to what? So now let's integrate this. So this is the integral from 0 to infinity of f of t, right? And now integrating this with respect to u, that is going to be differentiate this one with respect to u and then divide. So that is going to be negative 1 over t, and then e to the negative ut. Then you plug in the limits from s to infinity. You are done, and then you put the dt in the end. So this one is equal to the integral from 0 to infinity of f of t. And now let's plug in the limits, shall we? So the limits, we are going to have negative 1 over t in front here, and then we take the limit. So we are going to take the limit as u goes to infinity of e to the negative ut, like this. So like this, and then minus what exactly? So that is going to be e to the negative st, like this. That is plugging in the lower limit and the upper limit, and then dt. Cool, right? So this one is equal to, so I forgot, so the integral from s to infinity of f of u du. That is what we have. So the integral from s to infinity of f of u and then du, and this is equal to what? As u is approaching infinity, this one is approaching infinity. So this one is going to be approaching 0 because the exponent is going to be negative infinity. So 0 minus e to the negative st, that is going to be what? So the integral from 0 to infinity of f of t multiplied by negative 1 over t, and this one is going to be multiplied by negative e to the negative st, and then dt. So rearranging, then we are going to obtain our result. So this is going to be f of u du, and this is equal to the integral from 0 to infinity. So we are going to have positive e to the negative st, that is negative negative when you multiply them, and then we are going to have the function f of t over t, right? That is this t, and then dt. So now that is the definition of the Laplace transform of f of t over t. So the Laplace transform of the function f of t over t is going to be equal to the integral from 0 to infinity of e to the negative st multiplied by f of t over t dt. So that means that this one is the Laplace transform of the function f of t over t, and this is equal to the integral from s to infinity of f of u and then du. So now this is what we have. So that means that therefore our result, the Laplace transform of f of t over t, this is equal to the integral from s to infinity of f of u du, as proved. Alright, so now we can go back and then we check to see that this is exactly the same as what we wanted to find. Alright, now I'm going to use this result to show you some interesting stuff. So now I'm going to, how do you use this result to obtain a Laplace transform or something like this? Let me switch colors. I'm obsessed now with the switching of colors. So I'm going to find a Laplace transform of something like this. Sine of t all over t, right? How do you find the Laplace transform of this sine of t over t? So now we can use this one to show that the integral from 0 to infinity of sine of x over x dx is going to be equal to pi over 2. So that is what we call the Dirichlet integral, the Dirichlet, right? The Dirichlet integral. So how do we find the Laplace transform of that? So let's find the Laplace transform first, and then we can see how we will evaluate the integral. Okay, so now we will have this. So we are going to apply this result that we proved. So the Laplace transform of sine of t over t, this is going to be the integral from s to infinity of f of u du. So f of u du. But what is f of u in this case? F of u is the Laplace transform of the function f of t, right? So here in our case, f of u is going to be the Laplace transform of the function sine of t. So the Laplace transform of sine of t is going to be 1 all over. It's normally s squared plus 1 squared, but here you are using the variable u. So it's going to be u squared plus 1 squared, which is 1. So for sine of t, this is going to be a Laplace transform. So here our Laplace variable here is u instead of s. Alright, so this one is going to be equal to the integral from s to infinity of f of u, and f of u is going to be 1 all over u squared plus 1 and then du. This is the Laplace transform of sine of t all over t, like this. Cool. So now this is trivial. We can integrate this, right? This is the arctan of u. So integrating this one is just the tan inverse of u. And now the limits of integration from s to infinity. So the Laplace transform of sine of t all over t, this is equal to what? So now let's take the limit. So we take the limit as u goes to infinity of the tan inverse of u minus, you plug in s, that is going to be the tan inverse of s. So you can write it like tan inverse of s over 1. S is the same as s over 1, right? So as u is approaching infinity, tan inverse of u is going to be approaching pi over 2. So this is going to be pi over 2 minus the tan inverse of s over 1, like this. And this one is the Laplace transform of sine of t all over t. We can use this property, why not? So we know that the tan inverse of a over b plus the tan inverse of the reciprocal b over a, this is equal to pi over 2, right? So that means that the tan inverse of b over a, this is the same as pi over 2 minus the tan inverse of a over b, right? So now let me switch back. So this one here, what do we have? That means that the Laplace transform of the sine of t over t, this is equal to, so we have pi over 2 minus the tan inverse of s over 1. Using this property, we are going to have the tan inverse of 1 over s, like this. So the Laplace transform of sine of t over t is tan inverse of 1 over s, and this is the answer. So we are using this one, right? So this is what we have. And now how do you use this one to prove the Dirichlet integral? So the Dirichlet integral, let me remind you, the Dirichlet integral is that the integral from 0 to infinity of the sine of x over x dx is going to be equal to pi over 2. Now let's go down there and use this result to see how we can obtain the Dirichlet integral, the results of the Dirichlet integral. So the Dirichlet integral, let me do it in white pen. So the Dirichlet integral, so let me call that I. So this one is the integral from 0 to infinity of sine of x, so let me use t here, just a dummy variable, sine of t over t dt. So how do you prove that this result is equals to pi over 2? So now looking at this, how do you find the Laplace transform of this? So the Laplace transform of sine of t over t, let's use the definition. The definition is the integral from 0 to infinity of e to the negative st, right, multiplied by the function. So the function is going to be sine of t over t and then dt. Right, so this is the definition of the Laplace transform, and we just found that the answer is tan inverse of 1 over s. So this one is the tan inverse of 1 over s. Cool stuff, right? Now, what will be the value of s here so that this one will vanish, right? So if we are able to find the value of s here in which this one will vanish, leaving this one, then we can plug that one here to obtain the Dirichlet integral. Because if this one goes to 1, then I'm left with the integral from 0 to infinity of sine of t over t, and that is equals to the Dirichlet integral. So the only way I can have this one disappear while leaving only this is when s is equals to 0. So here we are going to put s to be equal to 0, right? So when we put s to be equal to 0, what do we get? So here the integral now reduces to what? So this is now going to be the integral from 0 to infinity of e to the negative. So this is now 0 times t, right? And then we have sine of t over t, and then dt, and this is equal to, so at the right hand side we are also going to put s to be equal to 0. So we are going to have the tan inverse of 1 over 0 like this. So now the integral I is equal to, so this is like the integral I, so that is going to be the integral from 0 to infinity of, when this one is 0, then everything here reduces to 1. So we are left with sine of t over t, and then dt, and this is equal to the tan inverse of 1 over 0. So 1 over 0 is like infinity, right? And what is the tan inverse of infinity? Tan inverse of infinity is pi over 2. So we have used this result to prove the Dirichlet integral. Very simple. So if you are able to establish that the Laplace transform of sine of t over t is equals to this one, then you can just plug in s to be equal to 0, and that will be the Dirichlet integral. So the integral from 0 to infinity of sine of t over t dt is going to be equal to pi over 2. Let me do another one for you to see. So this is question 2, right? So let me do another example. So example 2. So we are going to find a Laplace transform of this. So Laplace transform of the sine hyperbolic of 2t, and this is divided by t like this. So we are going to use the same result here. So the Laplace transform of sine of t over t, or f of t over t, this is going to be equal to the integral from s to infinity of f of u du. So let's write that. So this one is equal to the integral from s to infinity of f of u du. So f of u is the Laplace transform of the function sine hyperbolic of 2t. So let's write that. So f of u is equal to the sine hyperbolic of 2t. So the Laplace transform of that, I beg your pardon. So the Laplace transform of the sine hyperbolic of 2t, this is equal to 2 divided by s squared minus 2 squared, which is 4. This is so here we are using u. I'm sorry about that. So we are using u, so this is going to be u squared minus 2 squared, which is 4. So now we are going to replace that here. So I'm not going to write all this one all along. So this one is going to be the integral from s to infinity of f of u now is 2 divided by u squared minus 4, and then du. So we can do partial fractions here, why not? So this is the integral from s to infinity of 2 all over, this is difference of 2 squares, this is u squared minus 2 squared, right? So u squared minus 2 squared like this, and then du, and this is equal to the integral from s to infinity of 2 divided by u minus 2 into u plus 2 like this, and then du. So partial fractions, we can easily break this one down. Now let me do it here real quick. So I am going to simplify what this function will be. So if we have 2 all over u minus 2 multiplied by u plus 2, right, this is equal to, so we are going to have 1 all over u plus 2, right? So let me do u minus 2 and then minus 1 all over u plus 2 like this, but this one is going to be multiplied by half all the way in front. This is how you split it. So now let's see whether this one will be equal to this one on the left. So we are going to have 1/2, so 1/2 in front here, and then we can do cross multiplication. So we are going to have u plus 2 minus u minus 2, all this one divided by the LCM, and the LCM is u minus 2 multiplied by u plus 2 like this. What is the numerator simplifying to? Numerator is going to simplify to power 4. So I'm going to have 4 divided by u minus 2 multiplied by u plus 2. And then we will have to divide by 2. So the reason we are dividing by 2 is because we want to reduce the 4 to 2, which will conform with what we have in our original function. So this one is going to now evaluate to this. This one is going to evaluate to 2 into u minus 2 multiplied by u plus 2. Cool. So now this is what we have. So instead of writing this, I'm going to write this. So that is now splitting it into partial by using partial fractions. So that is going to be equal to the integral from s to infinity of 1/2, and then we are going to have 1 over u minus 2 minus 1 over u plus 2, like this, and then du. So this one, the Laplace transform is, now let's split this one into 2 different integrals. Why not? So 1/2, the integral from s to infinity of 1 over u minus 2 du minus 1/2, the integral from s to infinity of 1 over u plus 2 du. Okay, cool. So now integrating these ones are trivial. So this is 1/2. This is going to be the ln of u minus 2. And now this is going to be 1/2 the ln of u plus 2. All this one, the limits of integration are from s to infinity. Okay, so now this one, using the laws of indices, using the laws of logarithm and then factoring out 1/2 because it's common, that is going to be 1/2 and then the natural log of u minus 2 all over u plus 2, like this, and then the limits of integration from s to infinity. Now we can take our limits, why not? So this one is going to be 1/2, and now I'm going to take the limit as u goes to infinity of the ln of u minus 2 all over u plus 2. This is what I have for the upper limit, minus the lower limit. I'm going to have 1/2 the ln, just replace u with s, and now it's just going to be s minus 2 over s plus 2, like this. Cool stuff. Now this one, we are done with that. So the problem is this one. How do you take the limit as u goes to infinity of this guy here? So now in doing this, let me divide the numerator and denominator of this one, this function, by u. That is the highest power of the polynomial. So I have ln, and I'm going to have this. Divide top and bottom by u. That is going to be 1 minus 2 over u, right? All over u plus 2. I'm sorry, 1 plus 2 over u. Sorry about this. 1 plus 2 over u, like this. And then this one is done. This is 1/2 and the ln of s minus 2 over s plus 2. Now we can take the limit because ln is a continuous function. The limit can apply inside. So we have the ln of what really? So the ln of the limit as u goes to infinity of something like this: 1 minus 2 over u all over 1 plus 2 over u. You close this and then you close that, then minus 1/2 the ln of s minus 2 over s plus 2. Cool. So now as u is approaching infinity, this one is going to be approaching 0, this one is going to be approaching 0. So we are left with 1 minus 0 over 1 plus 0, which is 1 over 1, and 1 over 1 is 1. And then ln of 1 is 0. So this is going to be 1/2 ln of 1 minus 1/2 times the ln of s minus 2 all over s plus 2, like this. And this one is going to be equal to negative 1/2 the ln of s plus 2 all over s minus 2, I'm sorry, s minus 2 divided by s plus 2, like this. So using the laws of logarithm, this negative 1 here can become a power, so we can bring it out on top here. So this one is going to be what? This one is going to be 1/2 positive in front, the ln of s minus 2 all over s plus 2. So, and this one raised to the power negative 1. So raised to the power negative 1, we can just switch the fractions, and this is going to be 1/2 the ln of s plus 2 all over s minus 2, like this. Cool. So that means that this one, I'm not writing it all along, that was the Laplace transform of the sine hyperbolic of 2t over t. So the Laplace transform, so that means that the Laplace transform of the sine hyperbolic of 2t all over t. This one, the answer is 1/2 the ln of s plus 2 all over s minus 2, like this. Cool. So this is the Laplace transform of this function. So what if I'm asked to use this one to solve this integral? So let me use this one to solve this integral. So let's say we want to find the integral. So let's call it I for integral. The integral from 0 to infinity of what exactly? That is e to the negative like 3t and then multiplied by sine hyperbolic of 2t. All this one is divided by t and then dt. What is the answer to this? All right, so let me go ahead and write the definition of the Laplace transform of this. So let me do that here. So the Laplace transform of sine hyperbolic of 2t over t, right, this is equal to the integral from 0 to infinity of e to the negative st multiplied by the function we are seeking to transform, sine hyperbolic of 2t all over t, like this, and then dt. Is this one similar to this? And we just found that this one is equal to what? This one. So we just found that it is equals to 1/2 into the ln of s plus 2 all over s minus 2, like this. Is this one similar to this, right? Is it similar? So they are similar, right? So the only thing you have to do is to replace s with 3, right? Everything is the same. So everything is the same. T is at the bottom, sine hyperbolic of 2t on top, and then e to the negative 3t, and then e to the negative st. So the only difference between this one and this one is that s is replaced with 3. So this integral is just like this. This integral is just equal to 1/2 times the ln of s plus 2, but s here is replaced with 3. Right, so I'm just going to replace s with 3, and then that will be the resulting value of this integral, and that is going to be 3 plus 2 all over 3 minus 2, like this, and this is going to be equal to 1/2 times the ln of this is 5 over 1, which is equal to 5. So the value of this integral is 1/2 times the ln of 5, so, or 1/2 log 5. Yeah, so this Laplace transform is very important. You use it to solve very complex integrals that will be very difficult to solve on any given day. So this is the trick that I wanted to show you. So you see that this integral will not work for certain values of s, right? So the values of s cannot be less than 3. So if you put in 2, you are going to have like that is going to be 4 over infinity, right? 4 over 0, and that will be infinity, and this one diverges. So it can't be any value at all. It can only be for s greater than or equal to 3, and the integral will converge. So this is the trick that I wanted to show you. If you really enjoyed this video, you give me a thumbs up and then support my channel. And then I will continue uploading engaging tutorials on Laplace transforms. So in my next video, what I'm going to do, I'm going to talk about the Laplace inverse. How do you take the Laplace inverse of some functions? So you subscribe to the channel, and then I will see you in my next video. Bye bye.